Welcome to the second part of Erik's original two-part series. So this part is a primer on the generalized second law.
Thank you. So I'll be talking about the generalized second law today, if I can speak. So a prefatory remark about the slides. Don't freak out when the text slides appear with the slide count on the bottom right hand corner. It says something like 75. I clearly am not going to cover all of that material. I put a lot more in there than I plan to cover. Some I'm going to skip over. Some is at the end, because a lot of people asked me for the slides from last week. So I just put a bunch of extra stuff in there for people who want to see the slides, because it was really, really, really hard to restrict myself to a talk that would be 45 minutes long. There is so much material. This is such a rich, cool, fun, beautiful, sometimes glorious topic. I could probably give a week-long seminar on this and still not cover everything. So it was hard to choose. We'll see how it goes. So I will, as promised, because I didn't actually get to discussing some of the physical and philosophical musings about entropy last week, I'll just cover 3 of them very, very briefly. The rest are at the end of the slides for people who want to look at them. I'll talk about the motivation for the GSL, the structure of the proofs, the many, many different proofs for the GSL. I'll talk about what to me is maybe the most interesting consequence of all of this area, which is that in semi-classical gravity, it seems as though energy and entropy become much more intimately related than in classical physics or even in quantum physics by itself. And then conclude with some musings about the GSL. Okay, but I'm actually going to start with a quote from one of the great poets of the 20th century. I think I saw Klaus's window in the Zoom meeting, and I know Klaus loves Bob Dylan also. So this is for Klaus. And this may not be immediately clear to you why I think this quote is relevant, but I hope it will become clear as the talk progresses. Now, the Rain Man gave me 2 cures, and he said, jump right in. The one was Texas medicine, the other was just railroad gin. And like a fool, I mixed them, and it strangled up my mind. And now people just get uglier, and I have no sense of time. Oh, mama, can this really be the end, to be stuck inside of a black hole with the entropy and GSL blues again? Okay, let's get serious. So I'll discuss briefly the disanalogy of ordinary entropy with black hole entropy. Why it is that we seemingly demand that any statistical mechanical calculations rely on quantum gravitational degrees of freedom, and why it is that what we may learn from the fact that all QG programs seemingly derive, the A over 4 form of the entropy, or as I like to call it, the I'm always right problem. So the disanalogies. Recall I spent a little bit of time last week discussing how entropy in almost all physical theories has a modal character, and that in many different ways. It can be grounded in a principle that requires counterfactuals. It can be grounded in a principle that makes reference to possible rather than actual systems, and so on. But black hole entropy is not modal in that sense. It just is. It's a quantity that really is associated with a single state of, not a counterfactual possible set of states consistent with something else. And relatedly, there's an entropometer now. We can actually measure entropy directly. We just get a bunch of people around the event horizon, and they all, right outside the event horizon, and they all measure little pieces of area, and they all get back together and tell us what each one had, and we add them up, and we get the area. And also, it has a natural 0 point, like entropy for other classical systems. It's a short shield with mass equals 0. It also scales with the square of the mass, not with the mass itself. That complicates several issues in trying to work out a generalized thermodynamics of black holes beyond just the four laws. And in fact, the relationship between the entropy and the mass is even much more complicated in cosmological spacetimes, de Sitter and anti-de Sitter. Isentropic, a process as being isentropic does not imply that the process is reversible in any interesting way. Well, not just in any interesting way, in any way, I should rather say. That's a radical difference between entropy in ordinary thermodynamics and entropy for black holes. For every other kind of physical system I know of, it's possible to lower entropy by throwing in some mass energy. When I eat some food, it gets processed. I ate a bowl of oatmeal, very high entropy mush, and it gets transformed in my body into muscle and fiber, highly structured, organized systems. But not for a black hole. Any mass energy I throw into it always increases the entropy. And oddly enough, one of the foundations of ordinary thermodynamics is compositionality. How it is we can split and recombine physical systems. But you can't do that with black holes. I don't know of any way to split and recombine a black hole isentropically. So there are some really profound differences between black hole entropy and the ordinary entropies of other physical systems. Jacob?
So before we go to the next slide, going back to the previous slide. So last talk, I asked a question of entanglement entropy and honorific entropy. So we have a laboratory in our physics department downstairs, and they study systems of like 8 qubits, because that's about the state of the art at this point.
Even that's pretty impressive.
Right. They keep the system closed. It evolves unitarily. The qubits become entangled, and they experimentally measure the amount of entanglement. Like they have an entanglementometer, and they actually measure the entanglement. They compare it with there's been a whole bunch of arguments over the past 20 years trying to understand the approach to equilibrium in these systems, right? To actually see of the Boltzmann distribution show up in quantum mechanical systems evolved unitarily. When you trace out some of the degrees of freedom, the remaining ones begin to approach something like the canonical ensemble. There's a 0 point for this sort of entanglement that they can measure it. It's not that entanglement literally is entropy, but the volume of entropy is computed in this objective, deterministic-ish kind of determinant kind of calculation. There doesn't appear to be very much wiggle room in how the calculation is done. And it also doesn't strike me as particularly modal either, although that may depend on one's interpretation of quantum mechanics. But if, like many of the people working in that lab, and I've talked to them, they regard the quantum state as just a physical object that's become sort of spread around many different particles, and then they're tracing some of them out and looking at pieces of them, but they think that entanglement is like an objective feature of the system. To me, a little bit like what's going on with area and entropy, because we're not, I mean, I guess depending on one's view, we're not literally saying area literally just is entropy. That's a bit of an arguable point, but that it's tightly linked with entropy. We're not directly measuring the entropy, we're directly measuring the area. It does actually seem like there's a pretty close correspondence here, stronger than I think what I saw in your last talk. And I was wondering if I couldn't get this across because I was typing in I had a very narrow communication channel, right? Very, very, very bounded entropy in my communication channel. Now I have a somewhat larger modality, no pun intended. But if I was wondering if you could comment a little bit about that, especially because in your last talk, and of course, just knowing about the literature on black hole information entropy and entanglement entropy and QFTs, people keep coming back to this possible connection between the two. So I was wondering if maybe you could comment a little more on that. Why do we have to think of that in a modal way? Doesn't that kind of become a thing you can directly measure? Doesn't have a 0 point? It seems like in quantum mechanics, we do have something that might be a little more similar than I think maybe has been gotten across.
Oh, good. No, that's an excellent question and excellent point. well, I guess it was a point more than a question, but, well, it was both.
What's the question? I'm
It was
asking,
both. It was both.
is there more
Yeah.
information here?
So first of all, when I even on the slide, I said it has no natural 0 point for classical systems.
Okay.
So yes, of course, the von Neumann entropy has a natural 0 point. But in semi-classical gravity, we treat the black hole classically, not in quantum terms, at least in getting started, let's say. As to the modality that I see in the von Neumann entropy, so as you said, it's exactly right. Von Neumann entropy. It is obviously the ground for calculating von Neumann entropy. But in order to calculate the von Neumann entropy of something, you have to decide what the system is. And you have to carve up, your system into subsystems. And so the von Neumann entropy is something that is dependent on how you carve up your system into subsystems. Now, so in that sense, I don't think what you're doing is measuring the von Neumann entropy directly. You are, because in a sense, there's almost no such thing as the von Neumann entropy until you divide your system up into subsystems. To me, the tracing operation, so it does, I think you're right, depend in certain ways on one's interpretation of quantum mechanics.
And there are contexts in which it's definitely modal. For example, there's this distinction between proper mixtures and improper mixtures, right? People often align the two, but there are problems with the improper mixtures, which don't have necessarily a flat-footed modal interpretation.
Oh, I think they do, because an improper mixture is a statistical ensemble.
On some readings.
Oh, well, that's my read.
Right.
Okay. So at least on the reading of improper mixtures as statistical ensembles, I claim that there is a strong modality. I'm not claiming that that's the only way to understand it. That's just the way I understand it.
Fair enough. Fair enough.
Okay. So, yeah. Are we cool?
Oh yeah, we're always cool.
Okay. That's nice to know. So can these disanalogies, teach us anything about the form of a possible statistical mechanics that we would possibly want to underlie the thinking of black hole area as entropy? Because if black hole entropy is so different, at least in some ways, I claim, from ordinary entropy, presumably the underlying statistical mechanics can't just be flat-footed, straightforward Boltzmann or Gibbs or something like that. There's got to be some differences in what the statistical mechanics will look like in order to percolate up and manifest these differences. So that would be that may be a great virtue about these differences. But they may also, depending on your on your views on these things, maybe they militate against taking A/4 as a physical entropy. I lean towards the former myself. But I think primarily because BHT seriously, we need to think of the area as an entropy of some kind, and that should give us clues to how to move forward into a deeper underlying theory. And
Erik, this A/4, A is fine. Over 4, is it true that virtually every derivation always gets the 4, or is it a free number?
No. So the 1/4 is interesting because that holds in and only in classical GR, like modified alternative theories of gravity can derive a coefficient for the A, but it's never 1/4. If you get 1/4, you have the Einstein field equation that comes from the first law.
Right. Okay.
And so the almost all quantum gravity programs, in fact, see deriving the 1/4 as a necessary condition for their viability. And I think all the major programs have derivations that give you the 1/4. Some are more convincing than others. Seem like they might be sneaking some, underhandedly sneaking some things in that to make sure you get the 1/4.
Because I'm just thinking, classical, ordinary Boltzmann gas, the particle mass enters, for a given mass of gas, what's the entropy, it's the temperature, of course, but also the particle mass. So here, if to say that this is a kind of A/4 universal, is it like saying that there is one unit of mass, which is the Planck mass, and that's why I get this 4 and all theories have to get the same?
I think that's one way of thinking about it, is that there's a Planck mass, and that's why you get the 1/4. But not all derivations make that assumption or get the 1/4 in that way. Some of them do. So like the beautiful derivation of Sorkin, that's so elegant, from the 80s when he first introduced entanglement entropy in this context, gets the 1/4 in very much the way that you're talking about. But other derivations don't. But they all get the 1/4, or else they'd be dead in the water. So was I going to talk about that, or was that one of the things that I left to the end of the slide? I don't know. Let's see. I'll surprise myself and see what the next slide is. No. So a question that I have, I think it may still be coming up. I don't know. We'll see. So in ordinary statistical mechanics, you always calculate the entropy for ordinary system, classical particles, atoms, molecules, treated classically, just as little point particles. And you do the same thing even if you are doing statistical mechanics and non-relativistic quantum mechanics. You use kind of quantum point particles, so to speak. You never use quantum field theory to calculate the entropy of any ordinary body, any ordinary matter. So, and even if we were to try, say, to calculate the entropy of the air in this room using quantum field theory, we'd end up making so many, just to make the problem tractable, we'd end up making so many approximations and idealizations that at the end we would effectively be treating the air as something like point-like classical or quantum particles anyway. We localize the field's degrees of freedom in that way, or else the problem would not be tractable. So why are black holes different in this regard? We never calculate the entropy based on anything like classical or non-relativistic quantum or even relativistic quantum point particles or something like that. Everyone seems to think we have to go to QFT here. Is it? I think that it may be telling us nothing. It may just be kind of happenstance for various reasons, that this is how entropy is derived in various programs. But it may also, I suspect, I personally think it's telling us something again. If we can't find a way to do this using something like classical or quantum atoms, then again, the underlying statistical mechanics, I don't know why that word's so hard for me to say. The underlying statistical mechanics, I suspect, should be different in order to accommodate this fact. I don't know how. So here I will discuss the issue, Ramesh. So the issue of possible triviality. And this is not a problem that I originated. This actually, I did think about this and wonder about it, and then I came across this wonderful review article by Steve Carlip from 2014, in which he raises exactly this problem also. So essentially, every QG program derives, no matter how different they are, claims to derive the Bekenstein entropy. So it seems like it doesn't depend on anything that's peculiar to any quantum gravity program. So I think that if that's the case, then those derivations can't provide any confirmation to the QG program itself, because whatever is doing the work isn't something that's really part of that program in an essential way that differentiates it from other programs. And confirmation in this case has to be, I think, relative or comparative. So, and again, if that's the case, it seems like it becomes even a weaker than a minimal consistency requirement. It's just something that falls out kind of automatically if you have anything remotely like the right QG program. And the only way I see to avoid this is to posit that, in fact, all the QG programs do share some common structure. That's what's responsible for getting the A over 4. But I don't know any. There's very precious little evidence for that claim. If you want to make that claim, you are writing a very large promissory note, which I expect you to repay sometime soonish.
I have a related question. So there are some credible results from treating gravity as an effective field theory, right?
Yes.
Long range, degrees of freedom. People have calculated the first, corrections to Newton's law in the solar system. They've computed, two graviton scattering amplitudes. And these were all done in a sort of effective field theory for gravity. And presumably all the quantum gravity programs will replicate that result. And in that sense, it's not that we're giving them individually, credibility, but certainly if they failed to replicate that result, it would falsify it. Or at least we would strongly think that they're falsified, right?
I think that's right, yes.
So the fact that they all at least claim to get this right means that they all stay in the game. But you're saying that that's not enough. The fact that they're merely replicating, results that live in this intermediate regime between classical GR and the full theory of quantum gravity. It means they're in the game, but it doesn't really, because they're all doing it, it doesn't really give us switches.
Exactly. It gives no comparative advantage whatsoever.
Good.
But the first remark about the linearized quantum gravity. So I actually have a lot of problems with that program with regard to black holes, because I do not know how to model a black hole using the linearized Einstein field equation.
Was not referring to any black hole.
Okay.
They're very deliberately, right?
Okay.
All perturbative, weak field, nothing. Yeah. I mean, I agree with you completely about that point.
Okay. Cool.
Merely meant as not quite an analogy, but a little stronger, somewhere between an analogy and yeah.
Identity.
Sure.
Okay, let's get to the GSL. So what is the motivation for the GSL in the first place? Well, on almost any talk that's ever given on the second law, it's almost mandatory to quote Eddington, because it's just such a wonderful, marvelous quote. So I'm sure you've all seen it before, but you're gonna see it again. The law that entropy always increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists bundle things sometimes. I was really hoping Shep was going to be in the audience for that. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So we want to avoid collapsing in deepest humiliation. Most people do, I think. And that was Bekenstein's original motivation, pre-Hawking's, to save the second law. And what needs saving? Why does the second law need saving when there are black holes around? Well, it seems rather easy to violate the ordinary second law when black holes are around. John Wheeler, infamously in the late 60s, used to accost people in the hallways of the physics department, with a cup of tea in his hand and say, this is an entropic system. I throw it into a black hole. What happens? And Bekenstein, his grad student at the time, took up the challenge. So why is throwing a cup of tea into a black hole potentially problematic? Well, because you are decreasing the entropy of a causally isolated system, the world outside the event horizon, by an arbitrary amount. And it's a spontaneous decrease by an arbitrary amount. And it's not the same as in ordinary cases where, if we have a cloud of particles and one of them leaves the cloud and shoots off to infinity, then we ignore that for practical purposes and calculating the entropy. That's a practical issue. This is an in-principle issue. We cannot, outside the black hole, we have lost causal contact with the cup of tea. So how can it possibly contribute to the entropy outside the black hole? So it seems like black holes should be, entropy decreasers, the non-Perel. And so the second law, that most cherished of all physical principles, would collapse we would collapse in deepest humiliation because the second law would fail. So that's why Bekenstein proposed the generalized second law. He wants to attribute an entropy to the black hole itself. He has some very interesting arguments that conclude that the area of the black hole should be proportional, that the entropy of the black hole should be proportional to its area. He wasn't able to actually fix the 1/4, so this is slightly misleading, what I've written on the slide. But he definitely got it to an order of magnitude. Yeah, I think had log 2 as the coefficient. So the total area of the black hole plus the ordinary entropy outside, the so-called generalized entropy, that never decreases in any realizable physical process. And that is the generalized second law.
And, so you mentioned earlier that when typically we're counting entropy, we will be doing some derivations in point particles. Here in Bekenstein's derivation, one of the things he does is assign bits to area element, right? Because you're like, let's say you're working with vacuum black holes in vacuum GR, then would that be the equivalent of a, like a point particle, like an area element? Because it's geometry.
Yeah.
And the only other thing I can think of is gravitons. But like this, do you think this makes sense? Like as a
So on the general question, I do think it's an interesting question whether like thinking of Planck tiling of the black hole may be something like the point particles that you use in standard statistical mechanics. I think that's a viable possibility and something worth exploring. But if that really is what's happening, then still, Planck tiles are really quite different from classical or quantum point-like particles. So there's still going to be some differences that percolate up somehow, somewhere. On the specific issue of Bekenstein, so you're right. He was using bit counting arguments, which is exactly where the log2 coefficient came from in his formulation. But I'm actually going to comment on a few things directly on some of what you asked. So I'll say it and then see if you're satisfied.
Okay. There's a question in the chat.
Okay.
So Rahul asks how to include white holes in the generalized second law.
That is a very contentious and unsettled issue. So people have argued about whether white holes decrease generalized entropy or not for the past 50 years. Hawking infamously changed his mind on the point several times. Zurek thinks that white holes have exactly the same kind of entropy as black holes, and so they should be included. They don't decrease entropy. Other people think contrarily. It would take us really far afield to go into that. So Rahul, if you want to talk about it offline, I would love to. It's a fascinating question, but I'm going to put it aside for the purposes of this talk. I personally have no position on it. I'm really confused by it because it seems like the positions, both positions have some compelling arguments in their favor.
I mean, your first point on the slide is kind of an argument, right? We don't lack access to the interior of a white hole.
Yes. So according to Bekenstein's original argument, I think that's right. But there are other derivations of entropy in the GSL. It's not so clear that will be relevant. So, but yeah, as Jacob just said, so Bekenstein used information theoretic arguments. What the interior of the whatever's inside the interior of the whatever's inside the black hole is inaccessible to us. The information is effectively lost. So it's a measure. So the entropy of the black hole, the area, should be a measure of the information that is no longer accessible to us in the interior. And he said, even though I use quotation marks here, this is a paraphrase, not a quote of what not a direct quote of what Bekenstein said. He said, we can't know that the entropy inside is not decreasing or is decreasing. Either way, we can't know it because it's inaccessible to us. So it would be dangerous, epistemically dangerous, to just say, well, we don't need to attribute an entropy to the black hole. If we just add the entropy of ordinary matter inside the black hole to the ordinary matter of stuff outside the black hole, that will suffice to save the second law. And Bekenstein rejected that based on these information theoretic arguments. I think that his arguments they give extraordinary physical insight and understanding. I mean, it was an extraordinary theoretical advance. But when you really look at his arguments, they're pretty crappy. And I mean, even putting aside the information theoretic mess, because the way he used information theory was not quite under control. But I think it's a marvelous example of how bad arguments can, in not just in physics, but in math and philosophy also, can lead to real insight and advancement, because pioneer work is hard. If you're the first person doing something, you're gonna mess something up, but that doesn't mean that your conclusion is therefore, irremediably flawed. So the same claim, or actually more precisely, a similar claim, was defended by what I think are better arguments later on. A classic example for me is the 1982 Unruh paper called, I think, Acceleration, Radiation, and the Generalized Second Law, something like that. And they point out, which is also something also that Bekenstein considered in his original papers, that you can seemingly violate the Kelvin postulate, which, recall, says that there is no physical process whose sole result is that heat is extracted from a system at constant temperature and turned entirely into work. Because using Groucho's infamous example of slowly lowering a box from from infinity that's filled with radiation to the event horizon and then dumping it and letting stuff fall in, shows that if you could do that, that would seem to be a manifest violation of Kelvin's postulate, which is, to me, actually the proper statement of the second law, not the principle of entropy non-decrease. But I'll actually talk about that a little bit later. Their argument was, well, if you take account of the buoyancy of the box, because there's the Unruh effect near the black hole, because if you're slowly lowering the box, it's accelerating. It's not following a geodesic. So the Unruh effect tells you that you're going to experience some radiation from that acceleration, and that's going to provide a kind of a buoyancy effect. So the box will float, will reach an Archimedean equilibrium floating point above the event horizon. So you can't actually carry through Groucho's thought experiment. And so the Kelvin postulate, and therefore the second law, is saved. We don't have to collapse in utter humiliation. And it's QFT, on curved spacetime that saves the day. And interestingly enough, the argument, the structure of the argument, it's really subtle. It's not that you need the GSL. I'm sorry, it's not that just that you need the acceleration radiation to save the GSL. When you really study the structure of the argument, it turns out that the consistency, you need all the features of black hole thermodynamics working in tandem to preserve internal consistency, which is quite a remarkable claim, quite a remarkable conclusion for that argument. So it's not an argument for the GSL by itself. It's an argument that if we're going to take black hole thermodynamics seriously at all and so therefore we want some internal consistency, we must have the GSL in the form that we know and love it. I think that's a
so Erik, this kind of triggers something that Prashant and I were talking about just a few days ago. There is the second law, which says entropy, area, and all this stuff. And then there's Hawking radiation, which says, there is gravity, there will be some radiation coming out, what you call Unruh's, acceleration radiation. They look like two pieces. It's not like the coefficient 1/4 here has to necessarily imply so much temperature for the radiation, is our understanding. That, they are part and parcel of the story. And in fact, this whole floating and buoyancy stuff needs that radiation. That's what will stop the box. But are these, when you say they're all tied together, are they tied together to the point that for a given area, there has to be so much radiation, such and such temperature and things like that? Or are they really two tunable things here?
No, great question, and the answer is a little subtle and delicate. If you assume that the classical gravitational theory you're working with is GR, is Einstein gravity, then there is that really intimate and tightly coupled relation among all of the features. As soon as you modify GR, you lose that. And so, and the parameters do become independently tunable. So depending on your predilections, you may take that as a point in favor of using classical GR to ground black hole thermodynamics, or you may say, no, let's explore the other possibilities.
But again, you're saying under GR rules, just like the 1/4 is guaranteed, the talking temperature is also guaranteed. You
That's right.
cannot fit in with the coefficients.
That's right.
Okay. That's trying to understand that better.
But both of those essentially come from the form of the first law and the coefficients in the first law. And the coefficients in the first law are directly tied to the validity of the Einstein field equation. If you modify the Einstein field equation, you get different coefficients in the first law. And so that's, I think, to my mind, what I just sketched is the best argument in favor of the GSL. But it actually turns out it's an argument in favor of taking black hole thermodynamics kind of en bloc, seriously itself. That if we want internal consistency, we have to have everything. Which, in a way, it's actually like GR itself. One of the most beautiful things about general relativity as a theory is that there are all these different principles that are involved. Geodesic principle, conservation of stress energy, Einstein field equation, various features of conformal structure and relation to projective structure. And you can't just reach in and fiddle with one of them. GR is so tightly integrated that if you fiddle with one principle, you're going to change other principles necessarily. There's this really beautiful internal coherence in GR. And it turns out that possibly the same thing is true of black hole thermodynamics. So what are the structure of the proofs for the GSL? Because there are many, many, many different proofs and many different kinds of proofs. So this section will partially follow Aaron Wall's really beautiful 2009 paper, 10 proofs of the generalized second law. If you're interested in the GSL at all, that should be the first thing you read. And I really like this remark he makes, which I will follow. Here, a proof means a detailed argument trying to establish the GSL for a broad range of states in some particular regime. It's not a rigorous, he and I are not requiring a rigorous mathematical argument, not even necessarily an entirely consistent argument, just a good, compelling physics argument using physics math. So there are many issues to settle in trying to figure out what the particular state and particular regime is that Aaron mentioned in saying what he meant by proof. So first of all, not unsurprisingly, you have to choose what entropy for the black hole you're going to use. There are all the options: Gibbs, Boltzmann, information theoretic, entanglement, holographic. I actually should have added.
What's the other entropy?
Wald in 1981 has this really beautiful argument where it turns out that the entropy of the black hole is, in a certain sense, the Noether charge of the symplectic potential, and
right. It's like right. It comes from there. Right?
So I actually should have added the very first item on this list should have been Clausius thermodynamic entropy. I don't know why I forgot that. So then you have to decide which entropy for the matter to use. And only the first four in that list that I have above are viable for matter, although there really should be 5, including the Clausius thermodynamic entropy. What horizon are you going to choose? Because not every null surface is appropriate for a formulation of the GSL. So there's most derivations just use the standard traditional definition of an event horizon. The boundary of the chronological past to future null infinity. Some use apparent horizons, some use dynamical trapping horizons, some use horizons of black holes in cosmological spacetime, which really get more complicated. Some use so-called quantum external surfaces, and there are others that I'm not mentioning. These 5 are the ones that are most often used, at least so far that I've been able to, as I've been able to gather from reading the literature. And they all have their virtues and their demerits.
How does a dynamically trapping horizon differ from an apparent horizon?
Because a dynamical trapping horizon doesn't have to live in a traditional black hole spacetime. And just so strictly speaking, the definition of an apparent horizon and the definition of the boundary of a dynamical trapping horizon are the same. But just terminologically, people reserve the term apparent horizon for that associated with something like a traditional black hole, with a real event horizon. But a dynamical trapping horizon can live in a space-time without anything like a standard event horizon.
But it will become one?
No, not necessarily.
Right, Chaudhary doesn't guarantee that?
No. It's really, I mean, GR is weird. It always surprises you. But yeah, no, dynamical trapping horizons don't necessarily collapse into
What is
black holes.
Penrose's theorem then?
The
Singularity theorem.
So the reason why dynamical trapping horizons don't necessarily collapse and why Penrose's theorem is not applicable is because a dynamical trapping horizon isn't exactly the same as the trapped surface that Penrose uses in the singularity theorem.
Yeah, we should explore that a bit more. I don't get it. Yeah.
But you're right, they're so similar in so many ways. It seems like something like Penrose's theorem should work. And there are in fact some theorems that dynamical trapping horizons that have certain properties will necessarily eventuate in a singularity. But it's not entirely generic. Well, what regime are we going to choose? I'm not going to read this whole slide. But just to give you, I have it all on here because I want to give you a sense of how many possibilities, how complex the issue is. So following Aaron again, the choice of regime depends in large part on what restrictions the proof needs to impose on perturbations of the black hole. And that gives rise to two questions: how large and how rapidly changing these perturbations are allowed to be, and how many features of quantum mechanics are taken into account. I actually think more needs to be fixed, which is what kind of horizon, what kind of black hole you're dealing with in the first place, but that came up in the previous consideration. And then Aaron uses the answers to these questions to define two regimes. He calls the quasi-stationary and the quasi-steady. And also what he means by adiabatic. The first two are somewhat straightforward, but I don't have time to go into them. The third, the adiabaticity, is really subtle, and I'm not convinced by Aaron's discussion. I'm actually going down to see him at the Institute for Advanced Studies in a couple of weeks, and I plan to hash this out with him. So I would add to Aaron's list of questions, the two questions that set the regime, also that how are you going to deal with near horizon effects? Because a lot of these regimes implicitly, a lot of the proofs implicitly assume that all near horizons can be ignored, irrespective of the other issues of the regime. And then he uses the second question to find four further regimes, which got cut off. So in classical black hole mechanics, essentially in what he calls the hydrodynamic approximation, so it's things like the membrane paradigm, the semi-classical regime, full quantum fields on classical black hole spacetimes, and that bottom thing is cut off is full quantum gravity, although it's not really full. It's never full. It's always perturbated.
Like here, quasi-stationary, it looks like you're referring to the property of the metric.
That's right.
And quasi-steady is the matter.
That's right.
So in your 4.4.123, these are all quasi-steady only, with the background being exact.
So wait, I'm sorry, 4 point.
No, your bottommost, the regimes that we're looking at. Classical BHT, hydrodynamic.
Yes.
So these are all, the background is fixed to be stationary, not even quasi-stationary, but you have quasi-steady stuff happening.
Yeah, so that's not quite right. Sometimes they're not, so quasi-steady implies quasi-stationary, but not vice versa. Okay, I'm not gonna read all this again, but I'll just say you also have to settle what other space-time structures you're going to choose, whether you're working with an exact solution, whether you're using an abstract characterization that depends on kind of general principles. You want to know what the character of the quantum fields is, what formulation you're using, what flavor you're using, what boundary conditions you need, what your choice of state will be. You always need auxiliary conditions, energy conditions, entropy conditions, cosmic censorship, causal assumptions, and so on. So there's a lot you need to decide on before you figure out how to formulate the GSL and attempt to give a proof of it. Jacob?
I have a first order problem, and I mentioned this when I gave my talk, I guess last September. This also depends on how you think about quantum mechanics and how you think about what it means to have a fluctuation in quantum mechanics. If you have a tabletop system in a laboratory, an AMO system, a condensed matter system, I know how to interpret the axioms of quantum mechanics. I know what it means to, because we have this, we can employ a primitive notion of measurement. We have a measurement intervener, right? We have an agent performing measurements, and the theory predicts what this person will see. We often talk about stuff happening in the system. We talk about maybe the atoms are doing stuff, but that's all metaphorical. At the end of the day, the axioms of quantum mechanics say nothing about what's actually happening. All they do is render a prediction.
That's right.
About what measurement you'll get, with what probability you get that measurement, and you can average your measurement outcomes over measurement outcome probabilities. And we sometimes pretend that these averages are like the averages of classical system mechanics. They're averages over trajectories, they're averages over things happening. But once you get into GR, once you get into black hole spacetimes, I no longer have any understanding of what the fluctuations are supposed to mean. And people just take these metaphors that we use when we're talking about, tabletop systems, and they simply extend them to black holes where there are no observers, stuff happening on horizons, no one's doing any of these measurements. And I actually don't have any idea what's supposed to be happening here. And, if you go out on a limb and say that these expectation values in the semi-classical Einstein field equation, you are treating expectation values as if they're things just happening. On views where you can do that, you'll get some views where you can't. So to me, that's even prior to a lot of this discussion. I don't even understand how quantum mechanics is being used here. Very naive. What do you mean by fluctuations and perturbations in quantum mechanics here? I literally don't understand.
I think that's an excellent and really hard question. And I agree. I think it's shameful how much of really important foundational issues in quantum theory get entirely ignored in this entire literature. No one ever mentions the word measurement problem in any of this literature. No one ever discusses what they mean by fluctuation or perturbation. Well, that's not quite true, because if I can try and give a defense of the practice although I don't necessarily buy it, but I think this is what people would say. They'd say, look, we have quantum field. We have a quantum field in a vacuum state. We know how to calculate. We know what a 0 point fluctuation is for a quantum field in a vacuum state. You may balk at that in Minkowski spacetime.
When you say we know what it is, we can calculate mathematically a thing.
Yes, that's right. But that's good enough for that's good enough for government work.
I know what it means to predict this observable measure quanta coming out of the black hole. That's a thing that I trust. But everything else, I just don't even know what it means.
Right. Well, so I think that a lot of these people would say you're too restrictive in what we can give physical significance to, what we can give empirical content to. We should be able to give empirical content to claims that don't necessarily involve observers. And so we know how to calculate 0 point fluctuations for quantum fields in the vacuum state without making reference, as a mathematical fact, without making reference to measurements. And we will then assume that this can be given in physical content, although it may not be clear exactly what that is. Let's see how far we can get just using kind of vague physical ideas and these mathematical results, and we'll worry about the physical interpretation later.
I think it sounds like what they want is a better theory than quantum mechanics. And I'm in full agreement that we should.
Well, I think what they want is
the philosophical question of the measurement problem being really you can pave it here. This is a question where we actually do need an understanding of what the fluctuations are supposed to mean.
You're preaching to the choir, man. I completely agree. So what then is the generic structure of the proof? Well, there's not one. They're all over the place. They pick and choose from this enormous smorgasbord of possible conditions and structures. And because of that, the details of the proof, the structure of the proofs are radically different from case to case. And in fact, I couldn't resist I spent about half an hour working this out. At a conservative estimate, there are now, just combinatorially putting together everything that is, and I did it very conservatively, putting together all the things that are consistent with each other, all the different conditions and structures that are, interconsistent. There are 234,125,625,984 possible derivations. That's a lot. But clearly, a lot of them are, many of that fall under that number are probably physically meaningless or irrelevant in some ways. And so it's probably reasonable to focus on the relatively small number of derivations we do have. And that's what I'll do, just for the sake of practicality. I'll conclude with another wonderful remark from Aaron's paper. Most of the proofs are unsound. It's true, they are. Some have inconsistent or erroneous assumptions, and others have hidden gaps in the reasoning. Nevertheless, each of these proofs is valuable. Even an invalid proof can clarify the issues and choices that must be resolved in order to fully understand the GSL. Faulty proofs might also be correctable through small adjustments. It is better to view them as research programs than as mere fallacies. I think that's the most charitable and most interesting attitude to take towards the situation as it is. I think one could be, a real curmudgeon and say, no, this is all nonsense. There are all the derivations are unsound, which I think is correct. So I just don't care. I think that's not, manifestly, it's not an attitude that can just be rejected out of hand as deplorable or useless. I think it's worth considering that attitude. But I think at the end of the day, it is worth trying to enter more deeply into these research programs to see whether we can get something like a sound, internally consistent proof. So let's see, I have only a few minutes left. So would you all rather hear about the relation to energetic quantities and principles, or would you rather hear about some philosophical musings and speculations?
Let's do the energy.
Okay.
That looks a little more quantitative. We'll muse later.
Sounds good. Sounds good. Okay. So there's a really beautiful 2-page paper by the early 20th century physicist Richard Emden that on entropy. I really strongly encourage all of you to go read it. It's just beautiful. I actually learned about it because almost the entire paper is quoted in full in Sommerfeld's magnificent lecture notes on physical mechanics and thermodynamics. So it's not just that I love it. Sommerfeld also loves it. So that's a pretty good recommendation. And it's only 2 pages. Like, go read it. So, but Emden says, as a student, I read with advantage a small book by F. Wald. I asked Bob, and apparently there's no relation. I read with advantage a small book by F. Wald entitled The Mistress of the World and Her Shadow. These meant energy and entropy. In the course of advancing knowledge, the two seem to me to have exchanged places. In the huge manufactory of natural processes, the principle of entropy occupies the position of manager, where it dictates the manner and method of the whole business, whilst the principle of energy merely does the bookkeeping, balancing credits and debits. I think in classical physics, that's exactly right. But in GR, classical GR, and in semi-classical gravity, we have these so-called energy conditions that play an absolutely fundamental role. And it turns out that whereas there doesn't seem to be any clear relationship between them, there are some relationships between them, between the energy conditions and entropy in classical GR. Once you get to semi-classical gravity, they become really, really intimately and closely related and tied up with each other. And that, I think, has some really interesting possible consequences. So recall the energy conditions in classical GR. There are constraints on the measure of curvature, usually Ricci or Einstein, and they're given, and those constraints are given physical interpretation by invoking the Einstein field equation and rewriting the purely geometric condition as a condition on the stress energy tensor. And I think it's not too strong of a claim to say that there is a sense in which the Einstein field equation, just by itself, considered, without all the trappings of the rest of GR, it has almost no physical content. You can't, if all you have is Einstein field equation, you really can't derive any important consequences. You need something like energy conditions to give content to the relationship between matter and geometry. And essentially, every deep general theorem I know of in classical general relativity invokes an energy condition. There are very, very, very few, like 3 or 4 I know of that don't, and they're interesting, but essentially everyone does.
Not to be annoying, but I think the divergence of both sides of the Einstein field equation is a bit of view of conservation and stress energy tensor.
Yes.
Is that not physically important?
I think that's why I said it has almost no physical.
Okay.
But you can't even get, I mean, you do need conservation. Like when you're deriving the geodesic principle, it's conservation that plays the fundamental role. But you also need an energy condition.
Do these proofs typically use the strong energy condition, or?
No, the proofs for the different theorems use different theorems rely on different energy conditions.
The direct relation between the focusing seems to be more natural with the strong energy condition.
Yes, that's right.
But also it uses time-like conferences typically. So do you because the mass and the Hawking mass, for example, or the entropy, they're related to the mass and also divergence of photons. Would it make sense also to use something like the strong energy condition equivalent for photons?
Well, use the null energy condition for photons.
Yeah, but so do these use also the null energy condition as well? Quite okay. Okay.
So we're going to get to that right now, but just to complete the thought of this slide, even though you've probably read it, but it's worth saying, it's worth emphasizing. I think that the focusing of geodesics by way of guaranteed by way of the energy conditions is the single most characteristic role of energy in general relativity. And it's most characteristic of the energy conditions that one has one has a great deal of freedom in GR. So do people mind if I go like 5 more minutes? Is that okay? Okay. One has a great deal of freedom when one takes it primitive. One could take the geodesic principle as primitive and derive conservation. One could take conservation as primitive, derive the geodesic principle. One can't do that with energy conditions. There are no derivations of an energy condition in classical GR. They're always taken as primitive. So one might speculate that they seem to reach down and grab hold of something about space-time structure at a very deep level. This is not so of entropy conditions in classical GR. There are proofs of them. So Busso's covariant entropy bound relies on the dominant energy condition. Well, his original proof relied on the dominant energy condition. Very quickly afterwards, Flanagan, Marolf, and Wald produced a proof using the null energy. So entropy and energy do seem somewhat different already at the level of classical GR. You need the energy conditions to derive the entropy conditions. So there is some relationship between them, but it's so to speak one way only. There's no explicit unification of different types of entropy in classical GRs. There is as there is for energy, because and energy is most naturally and completely represented by stress energy tensor. All matter fields have a stress energy tensor. You can add them. Makes sense. There's still no entropometer because we're dealing with matter entropy. And the relation of both stress energy and entropy to equilibrium, as characterized, say, by the existence of a time-like Killing field, is completely obscure at best. And but it is interesting to see that energy already goes beyond in classical GR the role that Emden, the relationship already goes. Energy plays a more important role in managing the possible transformations and processes than it does in classical physics. So maybe we can say that energy is, if not the manager, it's at least the assistant manager in classical GR. Yes. So moving to semi-classical gravity, I think one of the primary motivating questions trying to figure out the relationship between energy and entropy is a question that Ted Jacobson very plaintively poses at the beginning of his really wonderful 1985 paper. How did classical general relativity know that the horizon area would turn out to be a form of entropy and that surface gravity is a temperature? Well, the first hints of more intimate relations between energy and entropy and semi-classical gravity are one. So if I had more time, I would have listed, I would have discussed all of these issues in classical GR. The differences between energy and entropy in classical GR that seem to disappear now. But you can probably work out for yourself what has changed for each of these ideas. So first of all, in classical GR, energy and entropy are not fungible. You can't transform one into the other. That doesn't make sense. But here, all of a sudden, they are fungible. Energy can be transformed into entropy, throw stuff into the black hole, the area increases. And vice versa, Hawking radiation seems to transform curvature into energy. It seems to transform entropy, which is defined geometrically, into stress energy. They now both have natural zero points, which is the same state. There are heuristic but compelling arguments that stationary black holes minimize one form of free energy and maximize entropy, which is just like in ordinary thermodynamics, but that doesn't happen in classical GR. And we have an entropometer, which is exactly the same as an ergometer, because when you measure the area of the black hole, you get the mass, which tells you both the energy and the entropy of the black hole. So, but the relations, including equalities between entropy and energy, go even beyond what I just stated. You get this really promiscuous, libertine, orgiastic debauch of relationships between energy and entropy. So again, one of the most, as I intimated before, one of the most natural ways to think of gravitational energy in GR, which is really kind of oddly unexplored in the literature, is by way of geodesic deviation. You extract work from a gravitational field when geodesics deviate, and stuff accelerates. That's the only way to extract energy from the gravitational field. But the only two attempts I know of to translate that into a calculation or definition of gravitational energy is this beautiful paper by Penrose in 1966 and some stuff I worked out when I was doing a PhD.
Are you counting Hawking this?
Hawking does not define a gravitational energy based on geodesic deviation. Not that I know of. And as we'll see, entropy now becomes associated with geodesic deviation, with focusing in semi-classical gravity. Indeed, entropy conditions now, in many of the most important theorems and papers, take on the classical role of energy conditions by guaranteeing geodesic focusing. So you get that the GSL proves the singularity theorem and other related results. You get that you get a quantum Penrose inequality based on the GSL. You get directly an idea called quantum focusing, which is a kind of a semi-classical gravity analog of classical geodesic focusing. So it seems as though entropy is not only playing its own roles from classical physics, it's taking on the character and playing the roles that energy used to play. And most interestingly to me about this is that the principle of entropy increase or non-decrease becomes fecund. It actually allows you to prove interesting results. Because in classical thermodynamics, quite weirdly, even though the principle of entropy non-decrease is so fundamental and central to thermodynamics, I don't know of a single general deep result that uses it as an assumption. It's incredibly useful if you're, if you want to figure out what the possible transformations are in molecular processes, say. It's incredibly useful in working out what the possibilities are for individual physical systems in given states. But I don't know of any general interesting theorem that uses the principle of entropy non-decrease in classical physics. But the situation has now changed. The GSL has really interesting, deep, powerful general consequences. I would really love to understand how and why that comes about. And one also has now not just has derivations of energy conditions, but derivations of energy conditions that are based on these entropy conditions. So I'm not going to explain what the quantum null energy condition is because it's a little complicated. I have it on the slides if you want to read it. But perhaps most intriguingly, one now actually gets equivalences, identities of energetic and entropic quantities. So you get that the quantum null energy condition is equal to second variations of the von Neumann entropy as used in the definition of the quantum null energy condition. And you get that the Bartnik-Bray inner mass, which is a quasi-local mass that's of some interest in GR, although it's mostly mathematical these days, equals the generally non-local irreducible mass corresponding to the generally non-local outer entropy.
So,
And
Erik, maybe this is going too far, but I want to stop you at that point. So in classical thermodynamics, when we kind of relate energy and entropy, there's always a temperature that comes in the middle, right? DE is TDS or whatever, there's a temperature.
yes.
So now let's say we look at the black hole problem. We have an entropy, A/4, fine. And we have a temperature, Hawking temperature. Original generalized second law never talked about a temperature, right? And that was a fine framework. And then Hawking came along and said, hey, wait a minute, does it actually radiate still? But is now the current thinking that this whole framework requires both an entropy and a temperature, and then you get all these deep relations between the two. That is to say, if somebody came and magically said, look, I can prove Hawking radiation is bogus. Okay, you can do all your calculations, but here is the simple argument why it just cannot work. Really, black holes don't radiate. Can you then immediately say you have to be wrong, or?
Well, so if you accept arguments of those like the Unruh and Wald argument I mentioned earlier in the talk, then yeah, if you don't,
About the lowering the
yes,
thing and the buoyancy and all that.
and that in order to
Yeah.
in order to not violate the relevant formulation of the Kelvin postulate,
Yeah.
you must have
Yeah.
both the acceleration radiation and the GSL working together.
Okay, that's one argument where
Yes.
it really helps.
Yes, but interestingly enough, for these, so for all of these results that I'm mentioning, if I remember correctly, and I think I can say with confidence that almost all of them make no reference to temperature whatsoever, or surface gravity, or anything remotely related. Some of them may, I can't quite remember, but I feel confident in saying that most of them don't.
But then how do they relate energy and entropy without a temperature? That's my question.
By way of the stress energy tensor, which does of the matter, which doesn't have, from which you can calculate the temperature if the stress energy tensor is the stress energy of, it represents the stress energy of a radiating field of Hawking radiation, but the relationship between stress energy and temperature doesn't enter into the proofs of almost all these results.
That is most interesting.
It
We
is.
should explore this further. Yeah,
I
would like
I
to
agree.
understand. Yeah.
So
Helen says time is up.
I know. So I will read this last quote by Maxwell and finish, and that will be it. Because I can't give a talk without quoting Maxwell, it seems. He's one of my favorite philosophers. Now, when the appearance of one thing is strictly connected with the appearance of another, so that the amount which exists of the one thing depends on and can be calculated from the amount of the other, which has disappeared, we conclude that the one has been formed at the expense of the other and that they are both forms of the same thing. He was taught in his beautiful book on the theory of heat from the 1870s. He was taught, this quote was specifically about conservation of energy. That all the different forms of energy related, associated with different kinds of physical systems are really all the same. There's just one quantity energy. But it seems as though, given these results are not coming out in semi-classical gravity, we're facing a very similar situation. And so possibly we should think of energy and entropy in a deeper theory as being different aspects of the same quantity. I will leave. So
Hawking temperature is real.
maybe. So I'll leave with that. I'll end on that speculative thing.
I think we should probably end it here. And
Yes.
people can feel free to have their time.
Yeah, please email me questions, for those on Zoom or we can arrange an appointment and talk. I would love to. And yeah, people here can call me. And how do we, there we go.
You'll be around here.